Good morning and welcome to the fourth lecture on the discrete math. Today we'll have two somehow interconnected topics. So we'll discuss a bit of graph theory, and also we'll discuss the sketch of proof of Cochlear Theorem, which was announced last time. So to start with, we'll remind what are the classes of P and NP. So the P class, which is the class of polynomial time solvable problems, is the class of decision problems for which there exist algorithms which solve them in polynomial time with respect to the length of the input in the worst case. So this means that for any input, the running time is bounded by P of the length of the input, where P is a fixed polynomial, so it does not depend on X, of course, it depends on the problem itself. And the class P denotes the class of polynomial solvable decision problems, which means that the answer should be binary, yes or no. So if you want to compute a function in polynomial time, the answer is not just yes or no, but something more involved, like Y. Then this class is not called a P. So this is not called a P problem just by format, by definition. And sometimes they are called FP problems, function polynomially computable. We will also come across such functions, and we already have seen them when we talked about reductions. But the P class is only the class for decision problems. So the NP class is also a class of decision problems, and there are several equivalent definitions. We'll use definition 1 today, and this means that we have non-deterministic computations. So the computation process can branch. At some point, there could be non-determinism. It could go via several directions, and there is the notion of angelic choice, that if at least one execution track of this algorithm yields yes, then we say that the answer is yes. So we should guess the correct branches each time we branch. Also, dual notion of demonic choice, where we have to succeed at each branch. This is co-NP. And the standard examples include situations where we have to guess something. For example, satisfy an assignment for a Boolean formula, say a 3CNF. So you just, when you don't know how to assign a variable to a value, you just rely on the angelic choice, which says that you should choose the right one. And if you check for a formula for being a tautology, then it is demonic choice, because you also guess your satisfying assignment, but if at least one of them is not a satisfying assignment really, then it will say no. So also existence of other properties like that is also an example of non-determinism. Like, for example, finding we'll discuss graphs in detail a bit later, but finding some easily checkable property of a graph is also NP, because you can guess this and then you check in polynomial time. So NP completeness, you will have the notion of reduction, which is M reduction or Karp reduction, and it says that you reduce A to B in the following sense. You say that you have the input, you perform some transformations with that input, and then you run B. So this is one of the most, say, strictly formulated notions of reduction, because here you run the oracle for B only once. So you perform some preparations and then you just ask B and you have to return the same answer. So you cannot say invert the bit. This is called M reduction, and the denotation is less or equal MP. So P stands for polynomial, M stands for the fact that it's M reduction, so these are not parameters, they are not say natural numbers or something. Just the whole symbol is the notation for M reduction. And why it is less or equal? Because if A is reducible to B, then A is simpler than B. Well, not harder. So this means that if you can solve B quickly, a good algorithm for B, then you definitely have a good algorithm for A, because it's just a composition of applying F and then running the algorithm for B. And The problem is NP hard if any NP problem is reducible to it. NP complete problems are NP hard problems which belong to NP themselves. So NP hard problems could be harder than NP. They could be even undecidable, for example. But NP complete is NP, and NP complete problems are the most complicated from the NP class. And if P is not equal to NP, which is highly likely but not yet proved, then we know that an NP complete problem cannot be polynomially solvable, because otherwise all other NP problems are also polynomially solvable. And Cochlear theorem gives a concrete example of an NP complete question, which is satisfying satisfiability of Boolean formula. So if A is an NP problem, then it is M-reducible to set. So the idea is that any possible situation of non-deterministic choice, but in the polynomial sense, so you have to make polynomial choices, and your algorithm should run polynomially, but non-deterministically. This can be represented as choosing a satisfying assignment. So the satisfiability problem is a generic NP problem. And let's consider an example. So we will consider a concrete NP problem, which is not set itself, of course, because for set itself it's trivial, it's reducible, and show how it can be reduced to set. And this problem will be three-colorability of graphs. So beware, if you know that three-colorability is NP complete itself, well, it is true. But what we're going to do now is not to prove that it is NP hard. We're going to show that that problem is reducible to set, but not vice versa. And first we have to recall what a graph is. So as advertised in the beginning of the course, a series of examples of discrete objects, well, besides Boolean formula and their satisfying assignment, is going to be the notion of graph and what happens with graphs. So we have to recall what it is. At the previous seminar class, we discussed graphs and even solved some problems concerning them. And now we will recall the informal and formal definition of graph. So an undirected graph, which will be the usual object for us, is a set of vertices, and some of them are connected by edges. So this is an example of an undirected graph. Directed graphs are also considered. Here we have arrows. So each edge has a beginning and the end. And here there are two ends. So they're symmetrical. So there are two special kinds of edges. You can have loops. Here is a directed loop. In an undirected graph, you can also have an undirected loop. And you have parallel edges, which connect two vertices. So they're the same vertices, but the edges are defined to be different. And by default, they are disallowed. And if you have parallel edges, it's called a multigraph. If you have parallel edges and loops, it's called a pseudograph. Oh, yeah. So yeah, there will be one typo in the further slides. I will notice that. And notice that if you have a directed graph and you have edges which go in different directions, they're not considered parallel. It's a normal situation that you have two edges which go in different directions. And there are many applications of graphs in representing all sorts of data which is structured as some objects and some relations between them. A very classical example of maps or geographical information systems. For example, vertices are cities and edges are routes that connect. This is a map of medieval trade routes from Wikipedia. And here the edges are colored, by the way, edge coloring, but not vertex coloring. This graph is not oriented because each route could be traversed in both directions, but in, say, modern situation, you can have streets or routes which are one direction, so which go backwards and forward. This would be an example of directed graph. Another example is chemistry, structural formula of molecules. Also, by default, undirected, but there could also be some directions imposed. And here, by the way, you can have parallel edges, because sometimes you will have, say, double or triple links between atoms in a molecule. Network topology represented by a graph, a standard thing. Linguistics, by the way, also. If you represent a structure of a sentence, it's usually some sort of graph theoretic situation, either a tree of structure or a graph of dependencies, as you can see here, or things like that. Social networks. It will be the standard example which we'll use in homework 3. In a social network, say here it's directed, usually say the friendship relation, say on Facebook of contactee is undirected, it's symmetric. So if you are a friend of another guy, then that guy is a friend of you. But also there could be directed edges, like you subscribe to some source of information or to some celebrity. That entity you subscribe to maybe even not aware of you, but this directed edge from you to that stuff. And many more. So graphs are important in data representation, where when we talk about data structured in this way. The formal definition is here. Well, this is not a pseudo graph. This is a graph with loops, but not with parallel edges. You have vertices, just an arbitrary finite set. Well, you can impose that it is non-empty, but you also consider empty graphs. And E is a subset of the Cartesian product of V on itself. So it's just a set of pairs of vertices, UV. Either you have an edge or you don't. And if the graph is undirected, then it should be symmetric. That means that if UV is an edge, then VU is also an edge. It's the same edge. And if you disallow loops, so it's just a normal undirected graph, then you have to make this irreflexive. So UU should be not allowed. So a symmetric, irreflexive binary relation on a finite set V is the same as being an undirected graph. For directed graphs, again, if you disallow loops, it should be irreflexive, but it's arbitrary, it is not required to be symmetric. So all other properties of relations are not imposed here. In particular, you do not require to be transitive. So if you have U to V and V to W, it could be not U to W. A friend of yours is not necessarily a friend of yours. And for multigraph, the definition is more involved because you need to consider parallel edges, and you cannot just say that an edge is just a pair of vertices. So that E is going to be a specific set, and for each element of E, you should just declare a function which says what are these edges or ends. Coloring. So you can color, in a graph you can color edges, you can color vertices. We're going to color vertices in colors over set C. C is a finite set also, or it could be infinite, but if you color only a finite set of vertices, you will use only a finite number of colors. So formally it's just a function from vertices to colors, and the usual what is called correctness condition is imposed, that if two vertices are connected, that the colors should be different. This comes from these old problems of color in maps, that if you have two countries which have a common border, which is represented by two vertices which are connected by an edge, then these countries should have different colors, otherwise they just link it. This is a just standard correctness condition for coloring, and it's represented like this. And an example is a three coloring. You have three colors, red, green, blue, and each vertex is connected to, is associated by a color. And for example, this graph is three colorable. You can correctly color it in three colors, and you see the coloring here. Well, this one is not. So why? You see that in the center here now I have a vertex which is marked with a cross. And around this vertex you have 5 vertices which form a cycle, a pentagon. So this pentagon is not colorable in two colors, right? Because connected vertices should have different colors, as we know. And here there is an odd number of them. So they should interleave, and when you cycle, you will get contradiction. So throughout these 5 vertices, you should have at least 3 colors. But then this vertex in the center should have the 4th color. Otherwise, there will be an edge which has the same. So 3-colorability is also an NP problem, right? If you have a graph, we don't know how to solve this polynomially. By the way, we will have a polynomial algorithm for 2-colorability, and this will be one of the tasks for today's exercise class. And we'll show 2 ways of solving that. But here, it's not clear whether it is a P problem, and it's not known. It's the same, P equals NP. But we know that it is NP. And this is easy because you can just non-deterministically guess the coloring and check its correctness. So each time the algorithm starts like that. Okay, we'll take the first vertex, we'll color it randomly, then we take any other vertex and we color it randomly. Unless it is connected to the first one, then we should choose another color and go on first and forth and forth. Either we fail, that at some point we will run out of colors and fail. It doesn't mean that this is not recolorable. It just means that we chose an incorrect strategy. If at least one of these strategies yields to success, we say it's recolorable and yields the recoloring itself. If no trajectory wins, then we say that it's not recolorable. So it's an NP problem. And there is a particular case of Cochlear theorem which says that this should be reducible to set. So what does this mean? It means that if you have a graph, then you can construct a Boolean formula which is satisfiable if and only if the graph is recolorable. The same will work for arbitrary number of colors, but for 3 colors is the first non-trivial situation. So 2 coloring is easier, and we'll see it on the example. So the reducing function from the graph to the Boolean formula should be polynomially computable, of course, because otherwise you can do the following. If you drop this restriction of polynomial computability, you can say, okay, we take the graph, we just solve the problem whether it is recolorable or not. This problem is NP, so it is decidable. You can just do brute force. You can just try all possible colorings. And then if it is colorable, we'll return something which is satisfiable, say constant true. If it's not, we'll return constant false. But this is not a good reduction function because it's not polynomial time computable. Or at least we don't know whether it is polynomial time computable. And our algorithm is not polynomial. So here it should be really a polynomial time function. It will be most natural. So this phi g will exactly represent the idea that a coloring, which is somehow encoded as a satisfying assignment, is really a coloring of G. So each 3 coloring of G, or correct 3 coloring, will correspond to a satisfying assignment of this formula, and vice versa. So this will be a one-to-one correspondence. And this is how it is constructed. So for each vertex Vi, we introduce the following Boolean variables, R, G, and B, which say that what is the color of the eye? It's either red or green or blue. And then this formula will represent natural conditions of these elementary propositions. So by now these are just variables, we don't know their meaning, but we will impose certain conditions on them. And this is how it is done. So the first line we say that each vertex is colored, so it's either red or green or blue. The second line, again, it's a big conjunction over all vertices. It says that no vertex can have 2 colors simultaneously. So if it cannot be red and green, so it's either not red or not green. And the same for other pairs. And finally, the third line is the correctness condition for coloring. The correctness condition says that if you have 2 vertices which are connected, they're not allowed to have the same color. So they're not both red, not both green, and not both blue. Indeed, this formula can be constructed in polynomial time from G. You just take G. For each vertex, you write down this guy, the first 2 lines. So for the first 2 lines, you just need to know the number of vertices and nothing more. And for the third line, you need to inspect all the edges. So how the graph is represented is, in a sense, up to you. You can represent it, for example, as a table of connectedness. So this means that you draw an end-to-end matrix, and each ik element is 1 if it is connected and 0 if not, a Boolean matrix. And you just inspect all this table and write down this formula. So again, the concrete complexity estimation of this is dependent on your representation of the graph, but if the graph is represented reasonably, it's indeed polynomial. It's like n squared or something like that. So this formula is easily computable and satisfying assignments of this formula in one-to-one correspondence with 3 colorings. So if you have a graph which is already colored, then you just assign the corresponding values to these variables. And if you can satisfy this formula, then from the satisfying assignment you read the correct coloring. So for each vertex you see whether Ri or Gi or Bi is true, and this formula guarantees that exactly one of this is going to be true, and this will be the correct color for the vertex. By the way, it's just 3 CNF. Well, it's just by accident, but it's nice. And why a CNF is good? Because what is a CNF generally? A CNF is a big conjunction. So when you try to impose many conditions on some object, where the object is the satisfying assignment, you will usually get something which is much like a CNF. That means that you have a conjunction of something. But these elements could be not junctions, that could be arbitrary, but here we're lucky it is a 3 CNF. And thus, if you could have solved satisfiability in polynomial time, we could also solve 3 colorability in polynomial time. In reality, this is of course not exactly the case. We do not know any polynomial algorithm for SAT, and reductions actually give us not positive but negative information. So these reductions are evidence against polynomial solvability of SAT. Why? Well, this works, as Cook-Levin says, not only for colorability but for any NP problem. So there is a large class of problems in the class NP, and if SAT were solvable in polynomial time, all these problems would also be solvable in polynomial time. But we don't know such an algorithm for any NP hard problem. So there are many problems in the class of NP for which we do not know a polynomial time algorithm. This means that this is an evidence that possibly there is no such algorithm. But it's all vague. So there's no formal theorem that P is not equal to NP yet. So therefore, this is just, if we believe in hardness of SAT, we also believe in hardness of 3 color. No, vice versa. If we believe in hardness of 3 color, we believe in hardness of SAT. And the idea of Cook-Levin is that any NP guessing can be represented like that. So you have an arbitrary NP problem, and it can be rewritten as guessing the satisfying assignment for a specific Boolean formula. But also these reductions can have some positive meaning. While there is no polynomial algorithm for SAT, the business of building SAT solvers is quite efficient. So there is a line of research and computer practice of constructing algorithms which try to solve satisfiability in a reasonable time. So it's not a polynomial, but nevertheless, sometimes it works. And one of the reasons is that we measure worst case complexity. So it means that there could be some complicated instances of SAT which are hard to solve, but some of them could be easy. So if your formula, say, is in DNF, you can easily solve it, right? If your formula is in 2 CNF, you can also easily solve it. Again, you apply resolutions. And again, for example, your formula is in 3 CNF. And we know examples that it could give you exponential blow up when you try to apply resolution. But this is not always the case. And sometimes, even if you have clauses like longer than 2, you can still have polynomial resolution time. So it's all dependent on the input. And there are also many heuristics which are used to optimize this search. Again, this does not yield a polynomial time algorithm properly, because possibly P is not equal to NP. But in practically valuable cases, usually these SAT solvers they work, and this is sort of competition in the international community to make them work better. And we have a reduction from a 3 colorability to SAT. So this means that SAT solvers can be used in a more generic situation, that if you have a SAT solver, you can apply it to other NP problems. And many people do this, for example, in genomics. So there are many NP problems concerning the genome and transformations of that, answering some questions. And there are Cook-Levin reductions to SAT, and they apply SAT solvers. And they say, by the way, that the really useful results happen to be easily solvable by SAT solvers. But this is just sort of informal intuition behind that. There's no formal grounds behind it, because really this is the worst case complexity is exponential, and no win of reducing it to SAT. But for SAT, who have already developed good heuristic systems, and you can use them for other NP problems. So this is the positive result from reductions to set. So okay, we return to Cook 11 now. Here we formulate it in this form that if you have an NP problem, then it is M-reducible to SAT. And now we have to formalize the following thing. We have to formalize what is an arbitrary NP problem. So for a concrete NP problem, we know that when we seek for existence of something, or we run a concrete non-deterministic procedure, and we rewrite it as a problem of satisfying a Boolean formula. But here we have an arbitrary computational process, and this arbitrary process involves non-deterministic choice, and we have to build a formula. Therefore, we have to concretize our model of computation. We have to concretize what does it mean for A to be solvable in NP. And this concretization, as we have seen at the previous seminar class, is Turing machines. Well, one of them, but it's what we're going to use. So, what is a Turing machine? Well, this is a formal definition. It's quite long, but it says that we have an alphabet in which our input is given. It's called sigma. There is gamma, which is the alphabet used internally. It's bigger than sigma. It could be bigger than sigma, so there are also other letters. There is a finite set of states, and there are starting, ending states, and a set of rules. So this is a workflow. The input is written on the tape, which is infinite, but at each time we use only a finite part of it. So in the beginning we write down our input word, then the machine works and it can't go beyond this. If and when it stops, we read the result. And in our case the result is just one bit. So it's 0 or 1. And we suppose that 0 and 1 are letters of sigma. So the rest of the tape, which is not used by the moment, is padded by blank symbols, which we denote by B, for example. And B is not in sigma. It's an extra letter which is used only in the computational process. The head, what they call it, or the computing unit of the Turing machine, holds the state Q. So inside your computer, in a sense, you will have a finite amount of memory. So it's like a finite automaton, if you know what it is. So, and all the infinite memory is on the tape. So it's very restrictive in its computing power device, because you don't have, say, random access to memory. You don't have infinite memory. You have only an infinite tape where you have to seek for the place where you keep your data. So for all the times, it was quite usual, even for real computers, to have such memory. Now it's something exotic, but nevertheless, it's easier to model such computations than to model real random access memory. The advantage of this device, if compared to a real computer, is that the memory is really theoretically infinite. So formally speaking, a real computer is actually a finite device, and you can actually represent it by just a finite set of states. It will be huge. It will be 2 to the power of the number of bits in its memory, where memory means everything. Random access memory, hard disk drives, registers in the CPU, etc. But formally speaking, it's finite. So what will happen if you try to perform computation which requires more memory than you really have? You will get an out-of-memory error. This is not what happens with a Turing machine. So a more realistic model of Turing computation is that you have a device which, instead of just halting with an out-of-memory error, requests the user to add some memory, like in a RAID disk array or something like that. So, and also we should have infinite indexing, so all happen like that. This means that the machine will be theoretically infinite. Again, in practice, of course, at some times you can just run of all the hard disk drives in the world, or even all hard disk drives which are possibly located on Earth or something like that. But theoretically, this is a model of infinite computation. So the rules work like that. You check whether you are in state P and observe A on the tape, And if it is true, then you perform the following transformation. You replace your internal state with Q, you replace the letter on the tape with B, and you perform a move. So the move could be empty, so it means that you just stay, it's N, no move. It means that you stay at the same point. Or you can go one cell right or one cell left, depending on the rule. And the machine is deterministic if for any P and A you have only one or not more than one such rule. So at each point the machine knows what to do. If there is no such rule, the machine fails. This is a failure of the computation. And once the machine runs into a state QF, it stops, and the word which is written on the tape is considered the output. So in our case, again, you observe 0 or 1. And you can say that if it is 1, then you say yes. If it is anything else, you say no. Okay, and in general, the trajectory can branch, and this is the non-determinism. Exactly. Also, the machine could stop unsuccessfully, which means that it didn't reach QF, but it reached a state where there is no state and the letter on the tape where there is no legal move. Then it just fails. It says, I don't know what to do. But also there is a possibility of infinite run, which says that it doesn't stop. So there could be, say, a state where you get stuck. In the world of polynomial time computations, this is not the case, because we always can say that we know the polynomial, this P, which is the upper bound on the number of steps. And if we know this polynomial, then if the machine exceeds this number of steps, we can just force it to halt. This means that it already failed, at least it failed to run fast. So we can say that, and this can be incorporated into the Turing machine, so we can say that in our polynomial computation, the machine always stops in polynomial number of steps. And therefore it always stops, and no infinite runs. But theoretically this is possible. And this is the rewriting of the NP class in the terms of Turing machines. So we say that it accepts that if there is at least one trajectory which yields yes, and if there is no such trajectory, then it says that it fails. And there is dual thing that the complement of an NP problem is not an NP itself, it's called co-NP. So if you want to flip yes and no, then you have to flip the quantifier. You have to, now we say that for any it means that if we yield yes at least one trajectory, then dually, if we want to yield no, we have to yield no on all trajectories. And it's a co-NP class. For example, the class of checking, the problem for checking that the Boolean Formula is a tautology is a co-NP problem. And SAT is an NP problem. So it's dual class. P is dual to itself, of course. Because if you have a deterministic Turing machine which just yields yes or no, then you can just perform its computation, but then flip the result. And you can always do this. But here it's non-trivial difference. Turing machine, they form a complete computational model by the following statement, which is called the Church-Turing thesis, that any computation on a reasonable computing device can be performed on a Turing machine. So this is an informal statement because the notion of being a reasonable computing device is not formalizable in any sense. So what does it mean? So possibly one can argue that we could physically create a device which is a computer, and such a device will compute non-computable functions. So there, of course, exist functions that cannot be computed, and this can be proved by just cardinality conditions. So for example, we have a decision problem. It takes an input, so an input could be just a natural number, and results in an output, which is yes or no. So it carves out a subset of natural numbers, and this subset is the set of all inputs on which we get yes. So the set of all satisfiable Boolean formula, for example. And there is a continuum of such possible sets, while there is only a countable number of algorithms of Turing machines. So there exists non-computable ones. So theoretically, there could be a physical device which solves non-computable, non-understandable problems. But for reasonable things, they could be reduced to a Turing machine. If you fix any other model of computation, this becomes a formal theorem. So, for example, you can say that, okay, I have a more involved computing device, like, for example, a formal definition of a programming language, like C, for example, with infinite memory and stuff like that. How can you reduce it to a Turing machine? Well, you can. This is hard, but you can. By many steps, you can reduce it to a Turing machine, which will compute the same function. It will run much slower, but nevertheless, it's possible. So for any fixed model of computation, the Church-Turing thesis becomes a tedious to prove, but real mathematical theorem. In general, it's an informal philosophical statement. And then you can concretize your definition of algorithm just by saying, okay, an algorithm is just a Turing machine. And this is useful when you want to prove something about algorithms. Not to construct an algorithm, but to say if there is an algorithm, then it has a certain property. Like in Cochlear Theorem, we say that if A is NP, so it's a non-deterministic polynomial algorithm, okay, then there is a non-deterministic Turing machine which runs in polynomial time. And there's also a polynomial version of Church-Turing thesis that if this computation on some computer was performed at polynomial time, there is also polynomial in the Turing machine. This one is much more questionable, and the modern state of art is that it's possibly even not true, because there are quantum computations, and there are problems which are solvable in polynomial time on quantum computers, which is the class QP. And the class QP is in between P and NP. So any classically polynomial thing can be also polynomially solved on a quantum computer, which means that quantum computers are at least as powerful as classical ones. Also, anything you can solve with a quantum computer is NP, so you can non-deterministically solve it. Actually, by replacing your quantum steps by just non-deterministic guesses and making it all classical. But all the inclusions are not known to be strict or not strict, so we do not know that QP is the same as NP. We do not know that P is the same as QP. So, but nevertheless, it's highly likely that QP is more powerful than P. So this is a polynomial version of the Church-Turing thesis only for classical computations. The degree of the polynomial could change, and we'll see that such examples in the class. That, for example, if you move from a Turing machine with several tapes to the standard notion of Turing machine with one tape, you will get quadratic growth. But it still keeps in the polynomial class. This is the robustness of polynomiality. So from now, when we prove Cook-Levin, we shall consider only Turing machine, polynomial Turing machine. So this is a proof sketch. So suppose A is in NP, and we want to show that it's reducible to SAT. So for each configuration of the Turing machine, we write it down as a binary word. So what happens here? The binary word is written in the bottom, but I will have to comment on it. So there is only one place where you have the Q. So this is the place which the machine observes. So Q is a finite, element of finite set, and elements of this set can be represented by words in zeros and ones, right? So we have m letters there. If there is a number of states is less or equal than 2 to the power of m, then we can represent our state as a word in zeros and ones of length not greater than m. Also, the binary word of m zeros will not represent any state. This will represent the fact that the head of the Turing machine is not observing the current symbol. So there is only one symbol AI which is observed by the Turing machine, and it's in state Q. And for others, we just have these paddings just for convenience of encoding. And also each letter, AI, is also encoded by a binary word. It's also basically the same. Here we also made some trick. We reduced all the stuff to a Turing machine which grows, the chain grows only to the right. This is equivalent to the classic one. It's technical, but you can try to do it by yourself. So this is more convenient just for the binary encoding, that it grows to the right, and when you reach the end of the tape where you have these B's, you just cut it off, because otherwise you would make the word infinite. So it's always a finite word which encodes the central part of the tape. Okay? So there are many details, but the general idea that the complete configuration of your Turing machine can be encoded as a binary word. And next, we say that there is a sequence of configurations, what's called a protocol of the run. So we start with the first one, where we write down the X, which is the input word, and each next is obtained by applying the rules. The rules are applied non-deterministically, so for a given X there could be many protocols of the execution. So, and it can be represented by a binary matrix of the following size. So you see that the number of rows, which is the number of steps of the Turing machine, is bounded by P of length X, right? Because we know that our computation should be polynomial. But also the width is also bounded by, well, it says m multiplied by P of X, it should be 2m multiplied by P of X, because we have states, we have letters, but nevertheless the total number of cells we could have used in our computation is also bounded by P of X. Because in order to access a new cell, which was blank, and put something there, we have to reach it. And in order to reach it, we have to perform the corresponding number of steps. And this number of steps is also bounded by the polynomial. So this means that this is a very big matrix of Boolean, it's binary matrix, matrix of Boolean values Bij, and this matrix is of polynomial size. And now we construct a formula, a Boolean formula, which expresses the fact that this is a correct protocol of a successful execution. So we will not, of course, write this formula explicitly. We did it already for the recording, it's enough. But nevertheless, we shall just show with the conjunction of the following claims. So the first row represents the configuration with X as the input data. Each next row is obtained from the previous one of the rules. It's also expressible as a Boolean formula, very big one, because the local transformation, we just say, okay, there is a place where we have our state, and we replace the corresponding letters which are the ones, according to our rules. And the last row should include the final state, and the answer should be yes. So this is the formula which represents it, and again, this formula is of polynomial size. Why? Because the size of the matrix is polynomial, and the size of the machine itself is fixed. So we are not obliged to be polynomial in the number of states, in the number of letters in the alphabet, and etc., because this is all fixed. It does not depend on the input. The only thing that depends on the input is the size of this matrix. And therefore this formula again is going to be huge, but it's polynomial size. And this is all expressed with Boolean formula. And we have the function that given an x, we write down this formula phi x, and we use, of course, all the things we had in mind about our Turing machine. Turing machine is fixed. And we know that this formula is satisfiable if and only if the answer to the original problem was yes, right? Because what does it mean that the answer was yes? It means that there exists a trajectory which returns yes, right? Which successfully ends and returns the answer yes. And in existence of such trajectory is the same as an existence of a successful protocol of the run of the machine on X, right? And the existence of such a protocol is the satisfiability, the satisfying assignment of phi x, satisfiability. And this yields Cochlear. And since A was taken arbitrarily, we get NP hardness of set. So satisfiability is NP hard, and this is the first concrete example of an NP hard problem. And SAT itself is also an NP, so it's NP complete. So it's a problem in NP, and any other problem in NP reduces to it. This is how the general reduction is performed. So at this point, we finish the sketch of proof of Cook 11. If there are any questions, please ask them now. If no, then we proceed to something a bit more specific. We know that 2SAT is polynomially time solvable, right? If your formula is a specific formula in a 2CNF, then it is polynomial time solvable by resolution. It was your homework number 1 to implement this. If your formula is in DNF, it's also polynomial time solvable. But translating the formula into DNF could yield exponential blow-up. Therefore, you cannot reduce SAT to DNF SAT. For 2CNF, there are even formulae which are not representable by 2CNFs. There are no equivalent 2CNFs. So this is again not a good reduction. For 3CNF, our resolution gives exponential blow-up, or potentially gives, and the question is whether 3CNF SAT is already NP complete. And this is going to be true. It's a special version of SAT where only 3CNFs are allowed, called 3SAT. Of course, it is reducible to SAT, just by trivial identical reduction. If you have a 3CNF, you can just use your SAT solver and solve it, so it's nothing more. But we need the opposite reduction. We'll show that SAT is reducible to its particular case. And then we'll have the following by transitivity. Any NP problem A is reducible to SAT. SAT is going to be reducible to 3SAT, which will mean that 3SAT is also NP hard. And 3SAT is the main NP hard problem usually used in practice. So let's show that. And the theorem is as follows. The theorem is due to Satan, that for any Boolean formula there exists an equisatisfiable 3CNF. And the size of this formula is polynomial with respect to A. So equisatisfiability means that B is satisfiable if and only if A is satisfiable. And this condition then equivalence. So of course, if two formulae are equivalent, then of course they have the same set of satisfying assignments in the IM or not. But equisatisfiability means that the formula B could have other variables that could be different from A. But nevertheless, its satisfiability is equivalent to satisfiability of A. And constructing an equivalent 3CNF is not always possible. And even translation to a CNF could give an exponential blow-up. But 3CNF there could be no equivalent 3CNF. It's a restrictive class. But equisatisfiability is available. For 2CNF, such things are impossible. So the Satan transformation is the transformation from A to B, from a formula to an equisatisfiable 3CNF. And it looks much like the translation into what they call assembler-like or 3-address code. So here we have an algebraic expression, A plus B multiplied by C plus D. And when you try to compute it on a real, say, machine, it will translate into something like that. Add A to B and put the result in T1. But T1 is an extra variable, extra place to keep things. Then add C to D and keep it in T2. Then multiply T1 and T2, and this is R, which is the result. What? So this is the translation of the following formula. And we'll do the same for Boolean formula. So for each subformula, we will introduce a new variable and write the corresponding equivalences. And then postulate that the variable which corresponds to the formula itself is true. Now here is an example. Yes?
So it's like
Yes, in a sense, yes, in a sense. Yeah, so not the YAC parser itself, but its semantic annotations. So when you parse your formula, you will have a node in your parsing tree, subformula connective on top, and for this you say, okay, I will introduce an extra variable for this new node, which is called P0 in the code, if you've seen the 2 lectures before. And then you say that P0 is somehow computed from the P1, P2, maybe P3, P4, etc. And here we have only P1 and P2, and we apply an operation, where the operation is one of these Boolean things. And here is an example. So when we parse it, we say that P implies Q is, say, T1, P implies R is, say, T2, then Q implies T2 already, so Q implies P implies R. It will be T3, and T1 or T3 is T4. And these are colored in different colors just to distinguish them. And these are all in conjunction. And the final thing is that you have to postulate that T4 should be true. This means that your Boolean formula is satisfied, right? The big formula should be true. Okay, so we claim that this is equisatisfiable with the original formula. Why? Well, suppose that our formula is satisfiable. This means that for some variables of P, Q, R, the formula on top is true. Then you can easily satisfy all these equivalences by just putting the values in Ti's as they are on the right-hand side. So you have P and Q, you know them, the concrete assignment. Then you just say T1 should be the value of the implication by a truth table. The same for all others. And why is it going to be a satisfying assignment? Well, because all these equivalences will be satisfied by definition. And in the bottom, you will have T4. And this T4 should be true because we know that this was a satisfying assignment for the original formula. So if you substitute it, it will give you 1. And it will satisfy this new Satan formula. And vice versa. Suppose you can satisfy the lower one. What does that mean? There is a satisfying assignment, and it satisfies, and well, it assigns some variables to PQR, and also it assigns some variables to these TIs. And we just take its sub-assignment only to PQR, and we claim that this is going to be a satisfying assignment for the formula on top. Again, why? Well, because due to these equivalences which are true, the variables of T1, T2, T3, T4 are going to be exactly the variables of the corresponding subformula, right? And we know that T4 is true because it's satisfied and it's in the conjunction, so it should be true. And therefore the global formula is true. So satisfying this long formula is the same as satisfying the short formula. But what is the gain? The gain is that this long formula is much like a 3CNF. So it's a conjunction, it's a big conjunction of short formulae. These formulae are not yet CNF clauses, there's our equivalences. But nevertheless, we can easily translate it into a series of clauses, and it's done as follows. So suppose that we have TK, which is equivalent to a conjunction. Then it's replaced by these 3 clauses, which means that what is a conjunction? It means that TK should be true if and only if both are true. Oh. Hello, on Zoom, on Teams, do you hear me?
Yes.
Yeah, great, okay, because something happened, but there's some activity here. Just a like, okay. Okay, great. So here it is. Yeah. So when TK is true, TK is true only if and only if Ti is true and Tj is true. So, and this says the following, that not Ti or not Tj or Tk. So if you can rewrite it like this, that if not Ti and if Ti and Tj, then Tk, right? So if one of these are not true, then Tk is also not to be not true. But if they are both, if both Ti and Tj are true, then the negations are false, and the first clause forces Tk to be true. And the other 2 clauses, they say the opposite implication, that if you have Tk, then you should have Ti. If you have Tk, you should also have Tj. right? Or if you are in doubt, you can just check these equivalences by truth tables. Just 8 possible cases. The same for disjunction, the same for implication, and the same for negation. So these elementary equivalences can be easily rewritten as three CNF clauses. Both implications. Conjunction of two implications. And on the right you can see these implications. So here you say, in the last line for example, tk is equivalent to not ti. It means that tk implies not ti, and not ti implies tk. And the first one says that not ti implies tk, and the second means that to. So, yeah, you should keep in mind that A implies B is not A or B. So if you have not Ti or not Tk, you can read it as Ti implies not Tk. Or dually Tk implies not Ti. But if in doubt, that this can be routinely checked by truth tables. If you do not want to try to understand this stuff in a logical sense, but you just wish to look at these guys and check whether they are generally true or not, you just say that okay, just check them by truth tables. Each line requires 8 checks, 2 cubed. Okay. And in our example, we get the following. So, well, just the colors are used to reflect the colors in the previous slide. So here we have this. Red goes to red, green to green, blue to blue, brown to brown, and the final T4 is just kept as it was. Now, this can be just routinely checked by these tables, and I hope that I'm not mistaken in this. Again, the 3 CNF, what can we say about that? It is longer than the original formula, of course, right? But it's equisatisfiable, as we know, because it is equivalent to that formula on the previous slide. The previous slide is equisatisfiable with the original one. And this is purely polynomial size construction, right? All the things we do here are polynomial. Nothing exponential happens. So what that means, we can return to this slide. So there is a reduction from SAT to 3 SAT. We take a formula, we perform Satan transformation on that, we get an equisatisfiable 3 CNF, and now what happens if we want to check satisfiability of A? It means that when we want to check it, we take A, we apply Satan transformation, and then we apply 3 SAT to this Satan transformation, to B, right? So if we can check satisfiability for 3 CNF, so we can solve 3 SAT, we can solve SAT. This means that 3 SAT is also NP hard and NP complete, which is a combination of Cook-Levin and Satan. Now, for the final part of today's lecture, let's discuss a bit of going beyond decision problems. So, and we'll concentrate on extensions on the NP class. Because for the P class, so we're not discussing broader classes like P space, for example. So we have 2 classes of decision problems, P and NP. So the P class can be easily extended to computing something more than just yes or no. We just say that there exists an algorithm, well, this Turing machine, which means which computes something in polynomial time, which is deterministic, and the workflow is easy. And for NP decision problems, its extensions are not that easy. So here we exercise the second definition of NP class, which is called the witness or hint definition. So the P decision problem is the question whether there exists a witness y such that R of xy is 1. We recall that what is the witness? For example, satisfy an assignment. And this R should be, so this witness should be polynomial size with respect to x, and R should be polynomial time computable. So in all our examples of NP problems, we had the following. So we guessed something and then performed a polynomial check. This was how it worked. What is a search problem? It is a bit harder than a decision one. And this was the second assignment for your home task, right? So the first home assignment, it had two parts. The first one was to check satisfiability. The second was to obtain a satisfying assignment if this formula is satisfiable. If not, it will just give you false or none or something like that. So it should yield a witness or say no. Again, in TrueSat, in satisfiability for two CNFs, this was also polynomially solvable. So it was NP, but it was also FP, and the search problem was also polynomially solvable. What happens here? For a general case, the NP, this is also, it's harder than the original problem, of course, right? Because if you know how to yield a witness, you can just ignore it and just return yes. Another class is the counting problem. The counting problem is to yield the number of witnesses. And finally, we could ask just to give you all witnesses. So, what about the second problem? How do you think, is it meaningful to ask for this? Even if P equals NP, could you solve it quickly? For example, for yielding all satisfying assignments, even for a 2 CNF. Could this be polynomial time solvable? It's a nice question, by the way. So again, the problem is like that. You can have 2 CNF, just as is in your home task, and you are asked to yield all the possible satisfying assignments. Could we do this polynomial time? Why? How can you do it? Yes, for each concrete satisfying assignment, you have a polynomial time algorithm. And this is the search problem. The problem is that the number of assignments itself could be exponential. So suppose I just do some stupid thing, I just give you just constant true, which is just the empty CNF. How can you yield all satisfying assignments? You should yield all the assignments. And this process is going to be exponential, well, not because it's something NP hard or something like that, but just because your answer is exponential. And therefore, it's unconditional non-polynomial. It's a rare case where you have a non-polynomiality result as is, not referring to some an unproved hypothesis, unproved conjecture. It's just exponential. So the next thing you could ask is a search problem. And actually, if P is equal to NP, then any search problem is also solvable in polynomial time. And this is done by dichotomy. So if your formula is satisfiable, you can take two possible cases for P1 and P1 equals 0, P1 equals 1. Find out which is satisfiable, then do the same for P2, for P3, etc., etc. And by Cook-Levin style reductions, this can be performed for any NP problem. So you should also be a bit careful about that, but search problems can be reduced to, and this is what you did actually in your doing now in your home assignment exactly, because but there is some extra thing that you have to. There you didn't just do these checks. You just said, okay, if in your saturation you don't have PI, you can put an arbitrary value. So search problem is basically the same complexity as decision one. And this gives a pointer. The counting problem could be harder than the decision one. There is an example. We'll discuss it in detail next time. So about one more consideration about the asking for all witnesses. What you could possibly ask is to yield all the witnesses but what they call is polynomial delay. So as we see here, you could not give an algorithm which yields all the witnesses in polynomial time, just because there could be an exponential number of them. But with the notion of polynomial delay algorithms, we do the following. So it starts working in polynomial time, so in time bounded by a fixed polynomial. It should either stop and say there is no witness, so no satisfying assignment, for example, or it should yield 1. Then it doesn't stop, it proceeds further, and again in polynomial delay it yields another 1, or says that there are no more. Again it delays polynomially, yields the next one, and up to the end. So this is a model of what happens with search engines, for example. So if you run, for example, Google or Yandex on this big data, which is all internet, all the web, ask for something, it would yield you some elements of this big amount of data, which corresponds to all the information of the world, and it takes the things which are in a sense satisfying you. So this means that they should be relevant to the search key. Of course, the amount of data which potentially corresponds to your searching key is very big. So it's meaningless just to show all of this in one screen. You will not have such time. But it will show you several results, and this is performed in polynomial time. And if you want more, then you ask for more. And again, the next portion of the results is given in polynomial time. It's quite fast. It works okay. And the difference from this, say, toy example is that in a search engine, there is some notion of prioritizing. Some of the results, some of the witnesses are considered better than the others, more relevant to your search question. Here, of course, all the assignments are equal in their rights, but also you can write an algorithm which does the following. So this is there. And it's, by the way, doable in the same way as here, but you should do, say, depth first search and find detail next time. So this is about yielding of witnesses and how these algorithms polynomial delay work with in the search engines. So for counting problems, this will be the topic of one of the topics of our next lecture. So this is about all for the lecture today. I will stop sharing. And I would like to announce several things about the home assignments and the grading for the course. So the first thing is that yesterday in the evening, I announced the second home assignment, which is the midterm. For those who are in class, you can take this in a physical printed version. For those who are on Teams, just look at the course's webpage. It is published there. The deadline is in a week, so it should be done just in written form. If you come physically to the class, you can just bring it physically as a written sheet, and I will grade it. If you are online, you can, or if you come physically, you can also do this. You can submit it by email, just as a scan or photo, or you can print it in LaTeX or in Word or something like that, as you wish. Anything which is human readable is okay. So this, I will check it by myself. Please bring it to the lecture, not to the seminar, because it's not Yakov's business to do this, it's my business. Okay, so this is the second home assignment. The first home assignment is still due, and I've seen people who are submitting it to GitHub. Some of you have submitted it already correctly, and the automatic grading system graded it as good. You will see this green checking mark that you are fine. By the way, when you clone your repository, when you start doing this, you will get these automated tests, which is called Boolean test.py. You can run it using PyTest, and check your correctness even without committing it to GitHub. But please don't forget to commit it in order for me to also to know this. You can do this as many times as you wish. So the Git classroom was configured so that you can do it anywhere. And once you get this green thing, you are fine. And I will actually look them up once more in the end of the after the deadline, which is next Tuesday, I believe, and see that this is that you are fine. So, by the way, if you are okay, then please do not commit anything more which can ruin it, because at the time I could see, maybe I could not note that it was correct. In case of any questions, please email me. Also, please submit by email. If you write it, say, not in Python 3, or you have some problems with the automatic grading or stuff like that. This could appear, but I hope that not for many cases. So this is about homework 1. And next time I will announce homework 3, which will be the final one. It will be a short programming assignment for 1 week. So the deadline for it will be the final class of yours. And this will all form to you cumulative grading. So the first home assignment has weight 4. I will put this information also on the course web page tonight. The second has also, the theoretical midterm has also weight 4. And the third one will get maximum grade 2. For the first assignment, there is a possibility of getting 2 if you solve only half of that. So if you get not, if the autograder says fail, I will still go inside and see whether the first series of tests pass. This means that you have solved the first half of that. About deadlines, they are designed to be strict. So if you have any problems with following them, please email me in advance, because otherwise just the grading roster could be closed and I will not be able to add something there. So if you think you will not come to deadline, and in that case you could get some points, but they will be reduced if you post it after deadline. But you have to inform in advance, otherwise it's impossible to get a good grade. There is also, so this forms a half of your mark. And there is also the final exam, which will be in your mid-session, what is called, after the classes. So I think it will be also on Wednesday. But since there are people who attend this course asynchronically from other time zones, I decided it will be as follows. We will take home for 24 hours. So it's not for a week, it's a real exam, it's not a home task, of course, but it will be published. I will write it down, of course, but the idea is that it will be published in the, say, 4 p.m. Moscow time on Tuesday, and the deadline will be something like 4 p.m. Moscow time next Wednesday, the next Wednesday after the classes. So for each time zone, you will have this time to solve it, so independently of where you start. So this will be also on the course's webpage. So this year, due to some changes in the regulations of the university, the final exam is going to be obligatory for all the students. Even if you get 10 in your cumulative grade, you will have to pass the final. Well, the reason is that there are some theoretical things which will be only on the final. They're not in the midterm and not in the programming assignments. So the final is, there will be problems like we solve in our practical classes, and also 1 or 2 theoretical questions. Please don't worry, these questions will be just for understanding of the notions. So you could be asked what does NP mean or something like that. You will not be asked something like prove Cochlear or something like that. This is just for your understanding of the course, but inside the final you will have such things. So this is some organizational information about what will happen with the grading, yes, and on Wednesday this will stop, and then on next Tuesday or Thursday I will have to submit it to the study office, so please keep it up. Okay, question?
Do we have to write answers on the exam in English, or?
Well, all the formulations will be in English. If you write it in Russian, I will accept it. If you write answers in Russian, if it's more convenient for you, it's acceptable. So my obligation is to provide all the material in English, but I can accept anything in Russian.
Will be better to write something in Russian, English, write down know that.
Well, but I actually guess where Russian starts and English starts in that case. Well, it should be understandable. It should be understandable. So it's, well, of course, reasonable. If you interleave words, then it will be strange.
I don't translate satisfiability because maybe I don't know where I.
Satisfiability is выполнимость in Russian. This is maybe the only word which you should know in Russian from this course. Which is not trivial. So if you say tautology, it's of course tautology, and if you say I don't know decidable, it is разрешимый. So it's, of course, since the course is in English, I don't give Russian terminology here because it will. Maybe if I have time, I will just publish a glossary for you. Or you can always. The good thing to do here is to use InterWiki. You can open Wikipedia. Oh. Oh, it's okay. You can open Wikipedia and find the corresponding article and then see how it is in another language, and you can see all the translations. They are usually fine. Not always, but usually they give the thing. Okay?
Role asks him all the time to equally graded.
I think yes. I think yes. That, but in the big ones. So if you have the 3 which has A, B, C, then they form a united one. But then these grades will be somehow normalized because there are 7 assignments here. You will have to earn 4 points, and well, in general, if you do all of them, you will get 4. But also, if you fail a bit, you can also get 4. Sometimes, well, it could be normalized to the top or something like that. So, and all the rules for this course that all the quotients they're rounded up. So, therefore, this could be nice. Yeah, I tried to make it as equal as possible, but they should have equal weights inside this grade. Okay, more questions, comments? Sorry, then thank you. And we meet for people on Teams. We meet just in 20 minutes on the seminar, and for other ones, then we meet next week.